this short video, we're going to talk about the expressions of nodes and branches and meshes, because they are the basic terminology when we talk about electrical circuits, and you need to know what these are in order to apply the formal methods of network analysis. We need to share a certain vocabulary when we talk about networks. And in order to set up node equations and mesh equations and also, let's say, analyze branch currents, you need to know what we are talking about here. This is the purpose of this video. Now, in order to compute unknown currents and voltages in a network, it is necessary to consider parts of the network in isolation from the rest. So we do not need to always consider the entire network, but sometimes we're going only to look at small parts and to apply various laws and rules to these individual parts. And we need to differentiate between the elements of a network in order to apply the equations which we have talked about in previous videos. For example, the node rule, the mesh rule, also the current divider and voltage divider, and all of these rules. And in order to do this properly, we need to share a certain terminology. We need to know what a node is, what a branch is, and what a mesh is. We also need to know that node and junction are interchangeable expressions, and also mesh and loop. So there's a bunch of expressions out there to describe a network, and this video is about introducing them to you so that you are sure-footed in when it comes to describing a network and applying the equations which we need to solve the network. And the approach we're going to use here is, first we will explain the basic terms, and then we will look at an example of setting up the mesh and node equations in a small example network. So let's start. First, let's take a look at a real net. This is a Fisher's net, little star here, C star, and also you can see this depiction of a mesh in this fisherman's net. So that's basically one of the sources where the terminology for describing networks come from. We have an electrical network, a circuit here on the right. We have seen many of these before, and if we look for similarities between the fisherman's net and this electrical network here, you can find that we also have a loop here. This loop is placed in between these three resistors, and as you can see here, this loop in the fisherman's net is placed in between these ropes, these lines surrounding it. So a loop describes a path through the net, and it starts from a certain point and it arrives back at a certain point, and it traverses these ropes here in the fisherman's net and these various resistors here in the electrical network. Now, this is called a mesh or a loop. And then we traverse, of course, all these various ropes here, and we do the same with the actual network. If you go from one such a junction point here to another one, this path in between is called a branch, and this is an element which you can also find here. So moving from one knot here to another one, the green line here indicates a branch of this network. And I've used the expression junction point or node, and this obviously can also be found here. It's where the knots are tied in a fisherman's net, and where certain directions branch off, hence the name. And you can also find such a point here in a circuit. At this point here, we have certain branches meeting, and when the current arrives at this node here, it divides up into various directions, and this is what's called a node or a junction point. We have plenty of these in networks, and in this particular network here we have 4 in total. So this is the terminology we are going to use when describing networks, and now you know where this analogy comes from, hence the fisherman's net here on the right. Now let's talk about a node in an electrical network. If you have at least 3 connections of circuit elements converging in one point of the network, such as shown here in this small excerpt of a network, and the current branches out from there, this is called a node. I have placed these measurement arrows here using the multi-sim simulator software, and we have a current of 3.125 milliamps arriving at this node here. We have a current of 1.875 milliamps leaving, and we have another current leaving here, a small one. Also, we have a potential at this node, 1.875 volts, and this is the information which, the set of information which a node provides. It answers the question what the electrical potential at this node is, and also which currents flow into the node and flow out of the node. And when it comes to setting up node equations, this is the information we can glean from a node, the distribution of currents, incoming, outgoing, and also the potential, the electric potential at this node. We can also transform a network at nodes. For example, this network here on the left, it's the example from the first slide when we talked about the fisherman's net. And you can see that we have a total of 4 nodes here, 1, 2, 3, 4. And since the potential at node number 1 and 2 is identical because there's no component in between where energy could be lost, we can simply combine nodes number 1 and 2 and also nodes number 3 and 4 into a joint node, because we do not change the distribution of potentials in this way. So we can simplify this network on the left by redrawing it in the manner shown here on the right. We have now a combined node called 1, 2, and also at the bottom node 3, 4. And this is much easier to deal with because you can immediately see that these 3 resistors are arranged in parallel. And in this network here, it's not as easy to see to the untrained eye when you start into this area of network analysis. So nodes help us to reshape, to simplify networks if there are no elements in between. Let's talk about branches. A branch of a network is a connection of exactly 2 nodes through 1 or more components. So we have a node here at top, we have a node here at the bottom, and in between we have, let's say, 2 components here on the right and 1 component here on the left. And this is what's called a branch, a path from one node to the other node with only a single conductor in between. And components of a branch, they have 2 connections, and the important thing here is there are at any place in this branch there are the same electrons coming through. It's not only the same current, it's literally the same electrons flowing through them. So every electron entering this branch here will come out at the other end, given that we leave the electron enough time to do so, because electrons, as we have talked about before, they move rather slowly. And a branch provides 2 pieces of information to us. The first is which current flows through it and also what voltage drops between the nodes. So we have current flow and we have voltage drop. And as we discussed before, voltage drop is simply the difference between 2 potentials. And as the information about potentials is provided by the nodes, we see this very neat combination, or this combination between nodes and branches where they meet. We combine the set of information which we get. Nodes provide potential and branches provide voltage, potential difference, and also current flow. Now let's talk about the third component in detail, which is called a mesh. A mesh combines several branches to each other, and we can form it by starting at a certain node, for example this one here, following the green path and walking back through the network on a closed path back to the point where we started from. It doesn't have to be a node. We can start somewhere in between 2 components in a branch. So it doesn't matter as long as we do not traverse through one part of the network 2 times, and as long as we come back to the point where we started from. And on the way through the mesh, neither branches or nodes, they, as I told you, may be considered more than once. The exception is, of course, the starting node where we start from. And the sum of the partial voltages, according to Kirchhoff's second law, along the path through the mesh must equal 0. So summing up all the voltages and also the source here at the end is identical to 0. And this holds for every mesh which we traverse, the green one, the red one, or any other ones, the other ones which we find here in this network. Now let's get to this very small example here. In this network we have 2 nodes, the top one, the bottom one. We have 3 branches, left one, middle one, right one, and also we have 3 meshes, the outer one, the left one, and the right one. And we can establish equations for all of these using the information provided by these parts of a network. And the equations established in this way, they form the starting point for the methods of network analysis we have seen so far. For example, we can use the branch current method, which is one method we're going to talk about in detail in the next video. Now let's summarize the major points we have seen so far. The first one is that in electrical networks we can divide them into the basic building blocks, nodes, branches and meshes. These terms are loosely based on a real net, for example a fisherman's net, and a branch connects components through which the same current flows. The node connects several branches that have the same potential at their connection point to this node, and then the mesh describes the path through a network, the circulation along several branches which are connected to each other, where the starting point corresponds to the end point. And the last one I'd like to share with you is that the basic components taught in this video, they form the basic vocabulary of electrical engineering and enable you, among other things, to go into this field of formal network analysis, which we will enter in the next video with the branch current analysis. That's all for this video. I hope you enjoyed it. If you have any questions, leave them in the comment section below. And I wish you a nice day now. See you next time here on The Fearless Engineer.